Hello there, this is Mr. Roche and Wilson as usual. Welcome to Mr. Roche's Flip Class, Math 10, low tech, low budget, no frills, no thrills videos. Today we're doing Relations and Functions Part 2. It's a continuation of the concepts that were covered in Math 9. In this particular episode, we'll be learning about linear relations. In other words, what constitutes a linear relation, how can we tell by looking at a graph or an equation or a table of values, as well as rate of change or slope. Wilson, I'm going to put you over in your spot. Wilson's going to run the camera. First of all, linear relations. There are many types of relations. Some are linear, some are not linear. In other words, they're curved or some obscure shape. We can tell if a graph is, or a relation is linear by looking at a graph. Okay? This is a straight line, it's linear. It's linear. Obviously it's not linear because it's not a straight line. And that is linear. Linear, linear, non-linear, and linear. Okay, it's just that easy. From a table of values, we have to look at the values that we have for the independent and dependent variables. In this case I used x and y, but of course it could be any variables in these places here. So if I look at the rates of changes, or how much each side goes up by. This goes up by 2, 2, 2. This goes up by 10, 10, 10. Because that rate of change is constant on both sides, that's going to make a straight line graph if I was to graph it. Therefore, that is linear. On this one, it goes up by 1, 1, 1. This goes up by 1, 3, 5. This side is constant, but this side goes up more and more each time. It's not constant. Therefore, that side would give me a curved line. Therefore, this side is non-linear. What about if we're looking at an equation? Here's some examples of equations. These two are in slope-intercept form. This one's in standard form. But we can still tell, easy enough, if they're going to be linear. The key here is it has to be in degree 1. The degree of this term is 1. The degree of this term is 1. The degree of this term is 0. We've talked about degree before in one of the past videos on it when we did polynomials. So the degree of the entire equation is 1. And if it's in degree 1, it's going to give me a linear relation. So this is linear. This is degree 1, this y. The 2x squared has degree 2, and this is degree 0. The entire equation here is in degree 2, therefore it'll be nonlinear. This equation looks different because it's in standard form, but again, degree 1, 1, 0. The entire equation is degree 1, so again, it will be linear. That last one, we should actually take a note that from an equation you can tell if it's linear or not by its degree. Degree 1, it'll be linear. Write that down somewhere. Okay, this time I'm going to talk about rate of change. And first we're going to do it from a graph, then from a table of values, and then from an equation. It's pretty hard to see the squares here, so Wilson, will you move up the camera a little bit to make it zoom in, please? Wilson? Oh, Wilson, use your hand. Oh, sorry. No hands. Okay, here we go. We have 4 lines on this graph, and we're going to try and get the rate of change from each one. First of all, let's do small Roman numeral 1, the blue one. What I'm going to do is I'm going to pick 2 places along that grid where the line crosses the grid at nice spots. In other words, not at fractions or decimals. So I could pick, say, this spot and this spot. Now make a right triangle that uses those 2 spots, either above or below the line. It doesn't matter. Now I'm going to use this formula. M, by the way, is the rate of change, or the slope. Rise over run. So this rise is 1, 2, 3, 4. And this run is 1, 2. So in this case, my slope is, the rise is 4, the run is 2. If I go from here, it's positive 2, positive 4. If I start here, it's going down 4, so it's negative 4, and then over negative 2. Either way, whether it's positive 4 and positive 2 or negative 4 and negative 2, I'll get a slope of 2. And we can double check it. It's uphill, so it's going to be positive. Okay? Going on to the green one. 2 points. Doesn't matter which 2 points. I'll choose these two. So the run is 1, 2, 3, 4, 5, 6. And the rise is 1, 2, 3, 4. Okay, so the rise is 4, the run is 6. So the rise is 4, the run is 6. I'm just going to reduce that down. Oh, there's a problem here. It reduces to 2/3. But my problem is, you see how it's downhill? That should be a negative. Now, let's see if we start at 1 point, if that actually works out mathematically. Here, we go down 4, so it's a negative 4. And we go to the right 6, so it's a positive 6. So that should be negative 4 over 6, which is negative 2 over 3. Had we started here, we would have went down 6 and up 4. And those signs would have been reversed, rather, but those would still work out to be the same. Okay. The red one here, if I chose that point and that point, the right triangle would be right along the line there. So we have, in this case, a rise of 3, but it hasn't moved left or right, so it's a run of 0. So in this case, 3 divided by 0 is undefined. So all vertical lines have a slope that's undefined. And finally, another blue one, this line. If I chose these 2 points here, 1, 2, 3, 4, 5, I have a run of 5, but no rise. So my rise this time is 0, my run is 5, so the slope there is 0. So in summary, if it's going uphill, going left to right, it's a positive slope. Going downhill, it's a negative slope. Vertical is undefined, horizontal is 0. And that makes sense if you imagine being a skier. If there's 0 slope, that means you're going to have to push your way along. However, if there's an undefined slope, you can be a good skier, but you can't ski it. You'll just free fall next to it. Ah! Okay. Sorry, lost my mind there for a minute. Okay, what about rate of change or slope if it's from a table of values? So in this case, it's how much the dependent variable changes as the independent variable increases by 1. Okay, you might want to reread that a few times. So this increases by 1, the independent. What does the dependent variable change to? Let me back up a little bit. Listen, will you get that? I had to help Wilson again. It's his hands. Okay, so this goes up by 1. This goes up by 10. So as this goes up by 1, this goes up by 10. So the slope here equals 10. Let's go to this one. This is also going up by 1. If we look at this, this one's actually going down by 5 each time. So the slope equals negative 5. And this one, it's going up by 5. This is going up by 50. So we have to do a little bit of figuring out. What if it only went up by 1? How much would that go up by? If you're thinking 5, you're right. But how can we figure it out? Well, we could use these to help us. But this is more grade 10-ish stuff, and you'll see a lot more of that this year. But your grade 9 teacher may have introduced it to you. So I could just take any two values of y and subtract them. That minus that is negative 50. And subtract these ones as well. This would be negative 5. Negative 50 over 5 is 10. So the slope again is 10. Oh, did I make a mistake before? I think I did. I think I said the slope was 5. The slope is 10. Okay. No editing in this job here. Finally, the rate of change from the equation. Okay? In this form, the slope-intercept form is what we call this. Slope-intercept, for obvious reasons that you'll soon see. M, this value, the coefficient of the x, okay, is always going to be the rate of change or the slope. So looking at these, the rate of change or the slope is the coefficient of x. Slope is 25. In this case, the coefficient of x, m equals negative 1. And here the coefficient is, or sorry, the rate of change is 3. Okay? And that's it. My next video will be part 3, and we'll learn all about the x and y intercepts. So, for Wilson and myself, so long for now.